Hi folks, today I have a lesson for you on Hess's law. Hess's law states that the total change in enthalpy is path independent. In other words, the amount of energy change for a chemical reaction can be determined by adding up the small miniature changes that results in the final product. So to explain this, we can understand, let's say we have a starting point on a potential difference scale. So we have, let's say, a graph here, and we have this is the potential difference, and so we have a point here. All right, and as the time goes by, let's say this person, which is at this level, has certain potential energy, and here this person climbs up a hill. And so the total change in energy of this person can be determined by looking at the difference in height. This is time, and the left hand side was potential difference or potential energy. And so the person was climbing up the hill, and so the initial point is this level here. The final height the person reached was this level here, and therefore the change in energy is that. Now, it does not matter how the person went from this point at the lower level to the higher level. So if I try to show you the diagram on the right hand side, let's say I show you the physical mountain, and this person starting here, or I should actually try to have the same height so you can see. So let's say this is the mountain, and there we are, and there we go. And then the height was starting point. It was this height here above the ground, so I'm keeping the same level here. And the final point they reached was this level here. Now, how did they reach this level? Now, when they went through the mount on top of climbing the mountain, they could have gone a nice linear straight path. They could have gone in an uneven path, or they could have gone down, around, spend their time, taken a few loops, gone there, and then reach the top. Now, it does not matter how they reached from the starting point to the finishing point. What is important is what was their starting point and what is their finishing point. That's what they mean by path independent. How the reactant converted into a product is not important. The amount of energy change is the sum of all the potential energy changes that the person has starting from the starting point and ending up at the finishing point. So if you're trying to calculate the change in energy, what we can do is we can add up all the small steps equations to find a target equation, and then we can add up all the energies that are required to get to those target reaction, and we will have the final change in energy of the reaction. Next, I will have an example for you so that we can see how we can manipulate the equation. So, when a chemical equation is given to us, we can manipulate the equation in two different ways. So, I'll show you this at the bottom here, manipulating the equation. And this is a very important skill for Hess's law problems because our equation may not be given in a specific format that is useful to us. So we may have to manipulate the equation to get it into a desired form, desired target form. So first thing that we can do to an equation is we can flip the equation. Okay, for example, if let's say we have A plus B forms C, and the change in energy is 30.43 kilojoules, we can what we can say is this is equation 1. Okay, we can manipulate this equation by flipping this equation. when we flip the equation, what happens is C becomes A plus B. And you see this is a flip of the equation because before it was a synthesis reaction. Now I have made it into a decomposition reaction. The reactants are now in the place of the products, and the products are in the place of the reactants. So I have flipped the equation. Now, when I flip the equation, I have to also change the energy. Before, if you see A plus B forming C, the delta H was 30.3 kilojoules. In other words, for this reaction, 30.3 kilojoules of energy was absorbed to form C. Now, if you flip the equation, what we are saying is C is decomposing to form A plus B. Now, in this case, if the previous case it was absorbing energy, in this format, the energy has to be released. So the delta H is changed to negative 30.3 kilojoules. Okay, so the delta H changes. So how do we change the delta H? The delta H is multiplied by -1. So the way to show this, so when you're writing on a piece of paper, how do you represent this information to the person who's reading it? What we essentially did is we took equation number 1 and multiplied by -1. Multiplying by -1 results in that equation where the equation is flipped. So C forms A plus B, and the delta H value, that was the 30.3 kilojoules, was multiplied by -1, which yielded a value of negative 30.3 kilojoules. Right? So that's how we represent it. That's how we write it down. So this is the format that we will write it down when we are flipping our equation. We will label our equation value as 1, 2, 3, 4, and then we can show the manipulation of each equation. And when we are manipulating the equation, we have to keep track of the change in energy, the delta H value. So that's one way of manipulating the equation, which is flipping the equation. The second way you can manipulate an equation is by multiplying the equation by a constant value. Okay, so you can multiply the entire equation by 2, or multiply the entire equation by 3, or multiply it by 4, or a fraction to get your target values. So, for example, let's say we have this equation A plus B forms C, which is delta H is 30.3, same equation that I had in number 1. Now, what I can do is I can multiply the entire equation by 2. So, what I can do is I can take equation number 1, and I can multiply it by 2. And what that does is it will make my equation 2A plus 2B forms 2C, right? So 2A plus 2B forms 2C because every coefficient was multiplied by 2. Therefore, but since everything has been doubled, the delta H is also doubled. So instead of 30.3 kilojoules, this will be 30.3 kilojoules times 2. And therefore, the value is 60.6 kilojoules of energy. So, two ways of manipulating the equation then. Right? And these are the two ways that you will be using to manipulate multiple equations so that when you add them up, you get your target equation. Next, I will have an example for you. But for now, these are the two ways. So, just recapping what we have learned in this lesson. Hess's law says the amount of energy change, which is the enthalpy of a reaction, is path independent. It is independent of the path. You can assume this as potential energy of a reaction. As climbing up the hill, the amount of potential energy is changed based on your starting height and the finishing height. It does not depend on how you reach that height. And therefore, same way in Hess's law, in a chemical reaction, the total amount of energy at the end of the reaction, or the change in energy, is dependent on the starting energy of the reactants and the finishing energy of the products. It is independent of the path that is taken to go from the starting point to the finishing point. You may go from start to finish in one single step, or you might go from start to finish in 50 different steps. The change in energy is the same. So that's Hess's law. And then we have learned two ways of manipulating the equation. The first way is to flip the equation. When we flip the equation, we are essentially multiplying the equation by -1. And so whatever values you have, they will be switched. The reactants become product, products become reactants, and the delta H is also multiplied by -1. The second way we learned was how to add, or sorry, multiply a coefficient or all the coefficients with a number. You can multiply all the coefficients by a constant value, and that will keep the reactions the same, it will keep the proportions the same. And when you do this, you have to also multiply the delta H by the same coefficient. That way, the equation is still valid, it is still maintaining its ratios and stoichiometric coefficients in the equation.